Hi guys, welcome to today's show. So we are starting a new concept which is trigonometry. So to start, we're just going to start with some investigation of what trigonometry is about, but in specific we're going to investigate triangles because that's the big thing that we're actually using under trigonometry. So let's just look at what exactly is a triangle, specifically a right-angled triangle, because that's what we are dealing with under trigonometry at this point in time. So let's just have a look at that and see exactly what it is about. Now, as I just said, we're starting with investigating triangles. So have you ever thought about, the very first thing, I always ask you questions. What do you know about triangles, right? And also, can I calculate one side of a triangle if I'm given maybe one more side? So let's say I have a triangle that is like this and I'm given this side, I want to find that. Can I find it? What will I need to use to do that? Or also, if I'm given two sides, so in the very same triangle, I'm given that one, I'm given this one, they want me to find this. Can I find it? What can I use to do that? Then lastly, is this true for all triangles? So are there special triangles where this can be done, where I can find one side given one side or given two sides? Or is it all triangles? Can I do that with each and every triangle? Remember, we have like 4 types of triangles, which I'm sure you're familiar with by now. Now, in terms of triangles, we call this a closed shape, right? So, they are closed shapes. They have 3 sides because of tri. They also have 3 angles. But now our concept map of what exactly we're going to look at, this closed shape that we want to talk about is actually a right-angled triangle, not just any triangle. We're going to specifically look at right-angled triangles. Also, we then gonna jump into Pythagoras theorem because of the right angle triangle, we can use the theorem of Pythagoras, which we'll look at a later stage. Then also we look at ratios of sides and angles as well. Then lastly, we're gonna talk about the concept of special angles and exactly what is it that they are about. But now let's just look at what right-angled triangles are. Now, our keywords here is right-angled triangle, the theorem of Pythagoras. I have what we call an adjacent side, which I will show you at a later stage what it is about. I also have what I call an opposite side, but I think with opposite, you kind of have an idea of what opposite means, directly across something. And also I have what we call the hypotenuse side, which we will also look at with the context of a right-angled triangle. Now, right-angled triangles are triangles that contain a 90-degree angle, and also they have 2 other acute angles, right? So acute angles meaning they must be less than 90 degrees. Remember that with a triangle, if you add all the angles, you must get 180 degrees. That's one of the properties we know of a triangle. So meaning these 2 acute angles can be 45, can be 50 and 40, as long as they add to 90 degrees, then we can consider it as a right-angled triangle. But the big thing actually is having the 90-degree angle. Now, the side that is opposite this 90-degree angle is called the hypotenuse side, right? And it is also the longest side of the triangle. But we're yet going to talk about all of that. But that's one side that you really need to make sure that you know. The only time I can see the hypotenuse side is if there is a 90 degrees that is opposite that side. If not, then you're not talking about the same thing as me. Now, as I said, the hypotenuse side is the side opposite the right angle. It is also the longest side of a triangle or in a triangle, right? So in this instance, the hypotenuse side will then be the side AB. Now, guys, one thing that you need to note about everything that I've said so far is with trigonometry, at this level that we are doing it in, we can only use right angle triangles and not any other triangles. But we're going to look at all of that, because remember the last question that I asked you was, is this true for all triangles? But now our main focus is just going to be the right angled triangle, because that's the big concept under trigonometry that we are looking at. Now, the two acute angles at vertices A and B, remember it will be this angle here and that angle there. But for now, I want us to only focus on angle A. And we'll also focus on angle B and talk about what do we see. If we focus on angle A, we can see that the side BC is opposite angle A, because remember we said our angle that we're focusing on is A. We also know that if we focus on angle A, the side AC will then be the adjacent side, right? So adjacent means directly next to, right? So that's what it will be about. Opposite, you know, it's directly across an angle or another side. Then we also have the hypotenuse side, which we've spoken about. Now, if you have all the sides according to the triangle, you can see that AB will be the hypotenuse, the AC will be the adjacent, BC will then be the opposite side of this triangle. Now, if we focus on angle B, the very same thing still applies. Hypotenuse is still the longest side, and it is also still the side opposite the 90 degrees. But now we have a different opposite. The opposite will be side AC, because it's directly across angle B. And then directly adjacent to or next to will then be the side BC, which makes it the adjacent side. So you remember those three sides that I wrote on my keywords? These are the sides that we are talking about. Now, just a quick revision of what a right angle triangle is about. It has a 90 degrees. There's a side that is opposite the 90 degrees, which is called the hypotenuse side. The other sides are named relative to the given acute angle. So remember, if it is directly next to the angle that we are talking about, it's the adjacent side. We normally use ADJ. If it's directly across, it's the opposite. So I can only name it with relation to the side that it is opposite to or it is next to in terms of the angles. So that's the main thing that we are talking about there. Also, remember that all sides are given the same letter as the opposite vertex. So meaning the side opposite A will be given the letter small letter A, right, as a lowercase. The side opposite B will be given a lowercase b. The side opposite C will be given a letter that is a lowercase c. So this is what I mean, A like that, B, and C. So you can see that whichever vertex that the side is opposite to, we name that side using a lowercase of that vertex. So this saves time from saying side AB. Instead, you can just say side C, you see. So it makes it a bit easier for us to talk about these sides. And then, so far we've looked at the right-angled triangle. In a right-angled triangle, only if it is a right-angled triangle can we then look at what we call Theorem of Pythagoras, which I just shortened it as Pythagoras. The Theorem of Pythagoras, it describes the relationship between three sides of a right-angled triangle. In specific, if we look at, there's an equation that shows this relationship. As you remember, I said we name the sides according to the opposite vertices. So the Theorem of Pythagoras here, if I maybe say it in words, it will be the square of the longest side is equals to the sum of the squares of the other two sides that are added together. So as you can see, it's a squared plus b squared. But you won't be required really to state it in words. You just need to understand the equation, because that's the main thing that we deal with. Now, that's what the Theorem of Pythagoras is about, right? And also the concept of a right-angled triangle. So what you guys need to know is, under trigonometry, you can only talk about a right-angled triangle. And with the right-angled triangle, you can then only talk about the theorem of Pythagoras. So meaning, you can see that the theorem of Pythagoras, if I was to ask the question, can it be used in any triangle? The answer will be no. Why? Because you can not use it if it's a non-right-angled triangle. So it's only if it's right-angled triangles that we are dealing with. Only then can we use the theorem of Pythagoras. So that's the main thing that I want you guys to take for now. Let's just go to a quick ad break and we'll be back with some more. Stay tuned. Hi guys, welcome back. So we are still busy with the concept of investigating triangles. So let's just quickly recap on what we've spoken about in our first segment. We looked at the theorem of Pythagoras, but because only when we knew that our triangle was a right-angled triangle. So the very first thing that we look at is if the triangle is right-angled or not. And then only then can we talk about the theorem of Pythagoras. We looked at the names of our sides in relation to the angle that they are adjacent to, opposite to, or the longest side of the triangle. But remember, the longest side must only be long and also opposite 90 degrees. Then can I call it a hypotenuse side, not only long, because remember some triangles, they do have longer sides, but they're not having a 90-degree angle. So just make sure that it is the longest side and also it is opposite 90 degrees in terms of a right angle triangle. We also looked at the concept of how can I find sides, right, given maybe one side or given two sides. Now we're going to talk about the concept of ratios to do that, because that's the main thing that we're going to be using in trigonometry to try and find an unknown side given one side and an angle maybe, or given two other sides and we want to find the other side given all of that. So that's what we're going to talk about. So now the main thing that we're looking at is the concept of ratios of sides and angles. Now, with a ratio is the comparison of two quantities of the same unit, right? So I cannot compare rands and compare it to kilograms. That will not make sense, right? So the ratio that I would want, if I want a ratio of rands is to something, it will have to be rands is to rands, kgs is to kgs, grams is to grams. So it must be two quantities that have the same unit. In trigonometry, ratios are given as common fractions or decimal fractions. So that means it can be given as 2/3, that's a common fraction, or it can be given as 0.5, which we know is the same as 1/2. So it can always be given as either a common fraction or a decimal fraction, depending on what the instruction is at the time. Remember, at times the instruction says round off to 2 decimal places or leave your answer in the simplest fraction form. You just need to look at what is the instruction at the time. Also, have you now thought about if there is a relationship between the sides and the angles of a right-angled triangle, right? So firstly, we looked at the relationship between sides, which we said was the theorem of Pythagoras. But now, is there a relationship between those sides and the angles of a right-angled triangle? What do you think about that? I just need you to be thinking about that as we are busy with what we're going to do, because that's the big idea that we are trying to answer with this investigation. Now, consider the triangle below, right? So you can see that I have the angle 30. I know what side A is. I know what side C is. Remember, the reason why it's A, C, and B, it's because it is a side opposite vertex B, vertex A, vertex C. So we name it according to that. The big question will be, what will then be the ratio of A over C? So that simply means I just need to substitute the value of A, which is 1. I divide it by the value of C, which is 2. So this is the same as 0.5, right? Common fraction, decimal fraction. Remember, that's what I said a ratio can be given as. Also, if maybe we look at a second similar triangle. Now, quickly, let's just do a quick recap of what similar triangles are about. Remember, similar triangles are when sides are in proportion meaning for us to get this side from this triangle to the other triangle, we will be multiplying by the same value or dividing by the same value to get one of the other sides from one more triangle. You see? So if things are in proportion with one another, meaning they don't necessarily need to be equal, as long as maybe they have the same angles, but the sides can be bigger. We call them similar shapes in just general. But in terms of triangles, it's when they have the same angles, but different sides in terms of lengths. And the lengths are bigger, one is smaller. As you saw, the first one had a 1 and a 2. With this one, you will see it has a 2 and probably a 4. And then the next one will also be a similar one, but the angle will remain constant throughout. So we'll look at that, please. Now, with this one, our ratio, which is still A over C, so we're not looking at what B is for now. We're only focusing on side A and side C. So A over C will be 2 over 4, which is the same as 1 over 2, which is the same as 0.5. So far, if we look at the previous slide, we saw that our ratio was 1 over 2. Even here, our ratio is still 1 over 2. Why? Because these are similar triangles and not just any triangles. Now, the third similar triangle below, now it has 3 and 6. Let's look at the ratio. If it's the same, then bravo, we are still talking about similar triangles. So the ratio will be 3 over 6, which is the same as 1 over 2, which is the same as 0.5. So you see, we're still talking about similar triangles. The fourth similar triangle, I just have my label A inside the triangle, but it is just really for this side. I just wanted it to be clear, hence I put it inside there. So please don't be confused and think it has to do with the interior of the triangle. No. Now here, our ratio, again, we're still looking at ratio, will be 4 over 8, which is definitely 1 over 2, which is still the same as 0.5. Now, what exactly do you know about this? We saw that our ratio is 1 over 2 for A over C. It was 1 over 2 for A over C for the second triangle. For the third triangle, it was also 1 over 2. For the fourth triangle, it was also 1 over 2. Why? Because they were similar triangles, and the angle was the same throughout, which really makes them similar. Now, the opposite of this, or the reverse operation, which we then call the reciprocal, right? We call this the reciprocal. It's when we tip and times our numerator and our denominator. So the ratio of C over A will be 2 over 1, which is just 2, which is just 2, 2, and 2 there. So you can see that the ratio is the same 1. The reciprocal is also the same, that's number 2. Now, what is it that we can conclude from seeing the ratio of AC and CA. We can see that they are reciprocals of one another. If we take one as the original ratio, the other one will be a reciprocal. I know you've learned a reciprocal at a very early age in terms of your grades and your maths. Now, in our conclusion, is our conclusion for the ratio A is to C true for the other ratios, right? What do I mean when I say for the other ratios? If now I'm comparing B and C, and I'm comparing C and B, also comparing A and B, what will happen? Will it still be the same ratio or not? So that's one thing that we will need to be able to answer, because remember, for you to draw a conclusion, it means that it must be general for everything that you are doing, because we are trying to have a general concept, remember, a model that we can use for all the triangles, given that it is a right-angled triangle. Now, I want you to please complete this table for me and just look at what will be the ratio of A over C if I know that the side B is root of 3. By the way, I got a root of 3 using the theorem of Pythagoras. So let's just quickly go back to this. Remember that if I look at this, right, so my theorem of Pythagoras will then be B squared will actually be C squared minus A squared. And C squared will then be 16 minus the 2 squared will be 4, and this will give me 12, and that's B squared. So if I want to find just B, it will then give me square root of 12, which is the same as square root of 4 multiplied by square root of 3, which is 2 root of 3. So what does this mean? Remember, when my side A is 2 and my side C is 4, my B will then be 2 root of 3. But I'm sure you are familiar with using the theorem of Pythagoras, because we did it as well at an early age in terms of our schooling career. So I want you to take some time and fill this table in. After filling this one in, you also need to then take some time and fill the second one in. Remember, here it's when we look at the reciprocals, right, of what the ratios are, because we looked at the first ones as our original ratios. But now what you need to then look at, what is the conclusion that you can make about the 6 ratios when the angle is 30 degrees, but the size of the triangles are different? Now, what am I talking about? The angles must remain constant throughout, but the sides can be bigger, others can be smaller, as long as the angles are the same. What deduction can we make about the 2 ratios, A over B and B over A over C, C over A over B over C, and C over B? What is it that you can actually make in terms of the conclusion between the two? That's the main thing that is going to assist us in seeing the bigger picture of what we are trying to do. So make sure that you complete those tables and look at what exactly can we say about those two comparisons in terms of 3, because it's 3 normal ratios and 3 reciprocals. So you can see that if you were to complete this, this is what it will look like. A over C will be 1 over 2 for all of them. B over C will be root 3 over 2 for all of them. And then A over C will be 1 over root 3. So that's not supposed to be A over C. It's actually supposed to be A over B. Apologies on that. And then you can also see that with the second table that I said you need to complete, it's just a reciprocal of what we have, right? So it's tip and times. The numerator swaps with the denominator. Hence, it's 2 over 1, 2 over root 3, and root 3 over 1. Now, what do we predict if the acute angle now is 60 degrees? What do you think? Also, if it's 45 degrees, what do you think? I want you to think about that. Remember, we've only been looking at the acute angle being 30 degrees. Now I want you to look at what happens if it's 60 degrees. What happens if it's 45 degrees? Will the same deductions that we made still hold, or will they be different, or will be there any variety that we're going to look at based on those deductions and those tables that I said you must fill in? You can draw them again with the same values and see what will happen in that particular context. Now, will the ratio remain constant for all similar triangles? That's the big thing that you want to look at. And then also, will the ratio, if you were to tip and times it, will it be the same as the original ratio? That's the big thing that I want you to do now. So as we go into an ad break, please try to investigate that. Draw 2-3 tables, fill them in, look at if the angle is 45 degrees, if the angle is 60 degrees. Remember though that the angles in a triangle, they must all add up to 180 degrees. So you can't have 60 and 60. It wouldn't make sense. So it will be 60 and 30. So it will still be in the same triangle as the one that we've been using. But if it's now 45 degrees for it to be 90, you know it's going to be 45 and 45. Just compare that and look at it. And then we'll be back. We'll talk about it some more just after the ad break. Hi guys, welcome back. So we are still looking at the concept of investigating triangles, right? Now, I gave you a task just before we went to the ad break to complete 2 tables and try and look at the comparison that you are seeing there and look at whether the ratios that we've kind of concluded with the first angle that was 30 degrees, will they be the same as well, or will they be constant with 60 degrees, with 45 degrees? And remember, I said 60 degrees will be in the same triangle as the 31, and 45 degrees will be in its own triangle, because at the end, the sum of the angles in a triangle must be 180. So that's one thing that I said you should do just during the ad break, so that you look at exactly, is this true for every angle, acute angle that is, because we are using 3 acute angles, 30, 45, and 60. Will it be the same for all 3? And we're going to look at what exactly is it that we are talking about when we say there's 3 angles that we are calling 30, 45, and 60. We're going to give them a name as well at a later stage, just to see exactly what is the bigger picture about these angles. So I hope you saw some similarities in terms of the ratios that I said you should do. You saw some differences that you saw in terms of the ratios that I said you should do, and also you could conclude something about it being constant or not being constant. But I hope you saw something that is worth seeing, because really there is something worth seeing there. Now, so far we've looked at the ratios of sides and angles. Now we're gonna talk about a special type of angle, which we call a special angle. Now, right angle triangles with special angles, they look something like this. So as I said to you, 60 degrees will be in the same triangle as the 30 degrees. This is really what I meant. You can see the 60 degrees there, there's 30 degrees, and my sides accordingly. One side that I didn't know was B, and I found it using the Theorem of Pythagoras. Now here, my letters are X, Y, and Z. You can see that the opposite ones will be the lower cases of the opposite vertex. If I'm given X and Y to find Z, I will use the Theorem of Pythagoras, which I believe you are also familiar with. The reason why this is 45 and that is 45, it's because it must add up to 90 degrees so that they can all be 180 degrees if you add them. Now, one other thing that I also need to mention here is with a 90-degree angle or a right-angled triangle, we normally show it with that small box there. So I don't necessarily need to tell you on the statement that the following is a right-angled triangle. I don't need to say that. As long as I say, look at the triangle below, and in the triangle you see this little square of mine there by the corner, definitely it is a right-angled triangle, because that's what we are using under mathematics to talk about a right-angled triangle. Now, you can calculate any of the 6 ratios for a given triangle with a special angle without a calculator, right? To link the ratio and the angle, we name each ratio of the 6 ratios. What do I mean when I say that? The ratios, we call them sine, we call them cosine, we call them tangent, and then we look at other 3 ratios, but we'll look at that just now. The ratio for any 2 sides is constant for a given acute angle for all similar triangles. Remember, that was the conclusion that we came to when we were looking at those 2 tables of mine with 30 degrees. And I hope you also maybe saw the same thing with the 60 and the 45. You can use a calculator also to find the angle if you have measured the length of the sides and calculated a ratio. So you can play around with this. Remember, I said the first one is if there is special angles, but now is when there is no special angles, we can use a calculator to do that, which we will also look at a later stage. To name the ratios, consider the right-angled triangle ABC with angle theta. So our main focus will be angle theta. That's our frame of reference. Now, if you want to look at this triangle that I have now, and I want to name these ratios, remember the definition of a ratio will be the length of the side opposite angle theta divided by the length of the hypotenuse. And this ratio becomes what we call the sine of the angle theta. In simple terms, it's sine theta is equals to opposite over hypotenuse. Now you will see some textbooks, they use the word OPP over HYP. It's really one and the same thing. Remember, we are smart as mathematicians, but our smartness makes us lazy at times. So we shorten things so that we can just, speak about them and not have to dwell into the language itself. Now, the other ratio is the length of the side adjacent angle theta. Remember, adjacent is directly next to it over the length of the hypotenuse side. And this will then give me cosine of the angle theta. In simple terms or in short terms, it's going to be cos theta is equals to adjacent over hypotenuse. Also remember, to make it short, it's ADJ over hyp. So I'm just including this because at a later stage, I might be just writing ADJ and hyp and not writing the whole word. So I want you to please be familiar with the vocabulary that I'm going to be using in trigonometry. Now, the last ratio is length of the side opposite angle A over length of the side adjacent angle theta, right? So this will be the tangent of the angle theta. Therefore, this is opposite over adjacent. Tangent is just the full word, but we call it tan. And then this is OPP, remember, over ADJ to mean adjacent. Now, the big thing here about these three ratios that I've given you so far is these are the main ratios that you're going to be using from now going forward with your mathematics career, right? If you pursue more maths in the upcoming years and all of that. So, we're going to also introduce the opposite of this, which we will then give a special name to them to say if it's no longer opposite over adjacent and it's adjacent over opposite, what is that? Or if we say we don't call it opposite over hypotenuse and we call it hypotenuse over opposite, what ratio is that? That's what we're going to look at as well, which will make it, remember, it's always been saying 6 ratios, 6 ratios. So the first 3 are what I just gave you now. We're just going to try and look at the tip and times of them, and that will introduce the next 3 ratios. Now, consider the right angle with now angle theta, right, also. If I say my sine, it will be that's my summary. My cos of theta will be adjacent over hypotenuse. My tangent of theta will be opposite over adjacent. So that's just a quick summary of what we've spoken about. Now, if it's now hypotenuse over opposite, right? Remember I said tip and times. We call this cosec. And in the full word for it is cosecant of theta. If our ratio is now hypotenuse over adjacent, we call it just sec. And this is secant of theta. Now, the other one also, if it is adjacent over opposite, remember tan was opposite over adjacent. Now we say we swap the ratios around, or the numerator and denominator around. This gives us what we call the cot theta, which is then cotangent of theta. Now, a quick summary of this, you can see my sine theta is there, cos theta is there, tan theta is there. And you can see I am kind of pairing them together with what they are related to, but we'll see what is it that they are related about. Here you can see my opposite is the numerator, there it's the denominator. Adjacent is the numerator, there it's the denominator. But it's still the same things that we are dealing with there. Now, what do you notice about the 6 ratios? Are there any relationships between them? What do you think? If I looked at my first 6 ratios, 3 ratios here, is there a relationship of those ratios with that? Kind of, because we saw that we're swapping the numerator and the denominator around. But what exactly do we call that? So we call these here the reciprocals. Remember, I was using the word reciprocal when I started here. We call these the reciprocals, and we call these the ratios. So these are 3 ratios: sine, cos, and tan. And then cosec, sec, and cot are the reciprocals of the 3 main ratios. And a reciprocal will be 1 divided by the ratio, and then the numerator and the denominator of the fractions, they swap because of the 1 divided by. But let's see exactly what does this mean. You can see from what I spoke about with summary, trig ratios here and reciprocals there. Now, with a reciprocal, you can see it's 1 over sine. So 1 over sine theta, remember it's the same as 1 over opposite over hypotenuse. And because I'm saying 1 divided by, these 2 will swap around, because that's what the big idea was. And this becomes hypotenuse over opposite, which will then be the cosec. So I hope you remember what we spoke about. With the 1 over cos, it's the same thing. It's 1 over adjacent over hypotenuse. Because of the one that I'm using as the numerator, my denominator as a fraction will tip and times, and it will then become hyp over adjacent. So that's what we are talking about when we talk about a reciprocal relationship. Now, for any right-angled triangle, you use the equation from the Theorem of Pythagoras to do what? To calculate the length of a side if you know the two sides. Remember what was my big question to you? Can I find one side given one side or given two sides, right? If I know the two sides, I can find the third side using the Theorem of Pythagoras. But what must be the condition? It must be a 90 degrees a triangle, right? So there must be a 90 degree in the triangle, meaning a right-angled triangle. So I can use that. So meaning, can I find one side given two sides? The answer is definitely I can. How so? Using the Theorem of Pythagoras. Now, the other question that I asked you was, can I find one side? If I'm given just one side, then here I can. For any right, I can use one of the trig ratios to calculate the size of the acute angle if I know the length of two sides. If I'm still given two sides, I can find the length or the size of the acute angle. So this was about the relationship that we spoke about in terms of angles and the sides of a triangle. Again, with a special angle, you use one of the trig ratio values to calculate the length of a side if you know the length of one side, right? So I want one side and I'm given one side, but I must also be given an angle there. So this answers the other question that we had that had to do with, can I find an unknown side given just one side? And is this true for all angles? Yes, because we are saying for any special angle. Remember our special angles, we did say that it's 30, 45, and 60 in that order, because they must be acute angles after all. So that's what we are talking about here. So meaning, so far we are answering the questions that we started with. And the first two questions that I asked you, definitely we can do it, because we'll use either the Theorem of Pythagoras or use the trigonometric ratios. That's what we can use so far. Now, for a right-angled triangle, although there are 6 ratios, a calculator only shows this one, that one, that one. So it only shows sine theta, cos theta, and tan theta. Then the other 3 ratios are the reciprocal ratios. Now, what does this mean? It means that I can only see sine, cos, and tangent. I think if you're on your calculator right now, any scientific calculator for that matter, I promise you, you will see them. They are written cos, sine, and tan, but it starts with a sine. I think it's the 3rd row when you just after your cursor on your calculator, on a scientific calculator that is. So just have a look at that. On your calculator now, press the sine, press the cos, press the tan, and tell me what you see. And then you will see that's what we are talking about in terms of the 3 ratios that we can have on the calculator. If I want to find the other 3, I will do what? 1 divided by sine, 1 divided by cos, 1 divided by tan, and that will give me the other 3 reciprocals. So make sure that you are familiar with this. So just on your calculator now and try and press these things that I'm saying so that you can just see it. And then in our next lesson, we definitely gonna dwell more into all of this. And I will show you exactly what do I mean when I say press this, and where do you find it in terms of your calculator. Now, the other thing is, remember we looked at the big idea, which was triangles. We're investigating what triangles are all about. Said it's when there is 3 sides, right? And also 3 angles. Those angles, they must add up to 108. In specific, we looked at one that has an angle that is a 90 degrees. So that was the main triangle that we're looking at and we're investigating. Because of a right-angled triangle, we can then use what we call the Theorem of Pythagoras, and that's only because there is a 90-degree angle in that particular thing. You can see, even if you were to go to Google and just look at the history of the Theorem of Pythagoras, it was only discovered because of a right-angled triangle. Now, from there we can look at the concept of ratios of sides and angles, and the ratios, remember the 6 of them that we spoke about, the main 3 that we can find in our calculator, and the 3 that are reciprocals. And then the last thing was our special type of angles, which we call the special angles, and those are 30, 45, and 60 degrees. Guys, I hope you've learned a lot in terms of how do we then look at the vocabulary and also look at the big idea of what trigonometry is all about, because that's what I've been trying to do with you here. We've been trying to investigate triangles. Why? Because that's the big idea of a trigonometric question at this particular level of ours. For now, I would like to say goodbye to you, and I will see you next time.